Starting with the great name of Allah, who is the most merciful and almighty. I am Usmanullah with my group member Muhammad Punal. Our topic of FIP is investigation and improvement of power quality issues in AC microgrid system. This was the topic of our FIP. So our literature review, aims and objectives, our view of the project, internal evaluation suggestion, methodology, conclusion and results, references. So aims and objectives. The aims and objectives that we have obtained through our FIP is maintain voltage stability, minimize harmonic distortion, ensuring compatibility with consumers. These are the objectives that we have to achieve through our FIP. Basically, we have 4 objectives in our FIP. So our view of the project, that what we have done till the end of the project is implementation of IEEE 14 bus system, which is used throughout the world for testing improved voltages. We have used both software GTAB and PSSC. Then we take the data of IVA, then we test it without DGs and DGs. We use different filters in order to improve the decrease the THD of the system. This is the data of IEEE 14 best system which were used for testing, and this basically it's the basic structures of the IEEE 14 bus system which is worldwide used for the testing. So implementing IEEE 14 system on both PSSC and ETAP, this is basically the PSSC system that we implement IEEE 14 bus systems. Now the question is why we have implemented this on both softwares, because we want to compare the results of the systems on both PSSC and ETAP. So this is the IEEE 14 system without DG inserted. Basically, we implement this on ETAP. The previous one was on for PSSC, and the next one is on the ETAP. Then this is the system without DG, which means that here the voltages we can see is about 83.332, 88.1, 91.7, 93.4. This is the condition without DG. When so here we can see that the voltages is basically 93.53, 97.13. These were the condition without DG. So when we placed DGs in the system, the voltages of the system is improved, but here the issue is that the harmonic of the system is reduced. In this system, we can see that it's reached to the THD is increased 10.1, 10 point something, which means that this is not acceptable according to the IEEE standard, because 5.5 or 5% is typically is THD is allowed according to the IEEE system. So basic function of the inverter. Now on the question, when the DG is inserted in the systems, it means that the THD is increased. Why the THD is increased? Because we have inverter when we are attached with the solar system which convert DC into AC, because we are in AC system. So in an inverter we have used the high frequency switching systems, which we use IGBT MOSFETs. They are the high frequency of switching, which leads to the high frequency waves. These combinations of the waves leads to the harmonics, and harmonic lead us to the THD, which means that this system introduced THD in our system. So we inverted different topologies, and these are the inverted different topologies: 12 pulse, 16 pulse, 18 pulse, and the 6 pulse is the most worst one. Why we are introducing here the topology? Because these topologies we have used in all system. They do how these topologies in our system can affect is if a person cannot support 18 pulse, which is expensive there. If he is using 6 pulse, then how it will affect his after inverter topologies, we take the Sakurai VA data, which Sakurai VA is generating through solar panels. Then this is the actual data that according to the internal situations, we take this data administration block. This is the actual data that they are actually using with this. We take this data and implement and implement this data in our softwares. Basically, this is the best extraction of the Sucker IBA, and that how their system is designed, that how their solar panels are used, and where they have placed. This is the basic structures of the Sucker IBA. So this is the PV system data, that which type of which they use mono, poly solars, both they have used. We also take this data, IBA inverter data. Then we implement this data in the tape. Now this is the condition without DG, when a Sucker IBA is not inserted in DG system. So what is the condition of this is THD. Here we can see that without the solar panel, the THD is almost to approaching to zero, but it's not zero, almost approaching to zero. So what is it means? It means that without DG there is no THD, THD in the system. So the waveforms, of course, waveforms are important for us. Voltage waveforms without DG. What it means, it's a clear sinusoidal current waveforms without DG. Here it's clear, shows that the waveforms are totally compatible with the equipment. So creations of harmonics with DGs. It means that when we introduce the DG in the systems, that they clearly affect the THD 11.11, kind of, as I mentioned earlier, that this is not acceptable in the IEEE 14 bus system. It's in the start with there was no DG, it was almost zero, but here it's totally approach to 11.11, which is of course not acceptable at 0.253. No one at each person, the THD is completely increased, which means that this is not acceptable. Why this is happened? Because we introduced solar panels in the so when we implement solars in our system, there is the THD of the buses according to the THD of the buses of the different buses. So when we implement DG in our system, of course THD is increased, and here it shows according to the bus that which bus have how much THD in the system. We show this in a bar graph. So after implementing, the waveforms is completely disturbed. As I have shown in the start, that this was sinusoidal without DG, but when we implement DG in our system, it's completely disturbed. Here it can clearly shows that the waves are not sinusoidal. Similarly, the current waveforms is also not sinusoidal, because it disturbs completely after implementing of the solar panel in the system. As you mentioned earlier, that we will use different topologies. Topologies means 6-bus topology, 12-bus topology, and 18-bus topology. Why we have used because it depends upon the money and budget of the man. In 12-bus topology, the THD is almost 5.33, which means it's lower than 6 pulse but higher than 18 pulse. In 18 pulse, it's reduced to 2.24. 18 pulse inverter is of course expensive, but its THD is lower. So similarly, if we compare the graphs in 6 pulse, it's completely disturbed. In 12 pulse, it's not as much disturbed, but in 18 pulse, it's like sinusoidal. So it's compatible with the system that in which system we are using our inverter. So after system design, the THD is increased, but we have to reduce this THD. For this purpose, we have designed the filters, and these filters were designed according to the IEEE 14 bus IEEE standard. So you will use C-type filters and single tune filters. These are the equations that we have used for our design, where C-type, where we are dealing with C-type, because it depends upon the requirements of the tape. In tape, we require different values. Like here we can see that KVR maximum, KVR micro we have required, because these values we have to calculate according to these equations. After calculating to these equations, we put these values in the tape. Then we get these results what we are wanted. But we also implement this on DSMOS because vary the value of n, because n is the harmonic, which harmonic you are going to reduce. these were the designing process of our filters. So we also implement this on the MATLAB, that where you are going to suppress which type of harmonics are going to suppress. So basically we implement this also on MATLAB. So this is the without filters. We do not implement any filters on the system. These were the conditions of the systems we have. We consider it's almost to approaching 11, 10.91, 11, which means 14.7. It means it exceeds the limit of IEEE without filters. So when we used single tune, because single tune filters, it reduced to 9.9, 9.75. First, we implement this on IEEE 14-bus system because we are working on two systems. Then we implement this on ISACR system. In here, we target just the first harmonic, the fifth harmonic, because in the we targeted different harmonics to reduce the total THD. In this, we have targeted just the first one. So using single tuned. When we used again the single tuned system in our system, that it's reduced to 4.02. It depends upon the bank. When the bank increases, the THD of the systems also increases because we use more filters and reduce the more harmonics. So similarly, we target other the fifth, seventh, 11th, and defect harmonics. So it's the waveforms. Then using C-type filters, of course, we implement C-type filters that reduced the THD. As I mentioned, you use both C-types and single tune. Here we want to show that both of our filters are working completely because it is used to 8.0, so 8.33, 8.71. In the starts it was 11 point something. Now the total reduction depends upon the banks, that how many banks of the capacitors you are using. So suppression of the fifth, seventh harmonic, as I mentioned, with different we suppress different harmonics of the system first. So C-type is a voltage waveform, of course, voltage waveforms and the system. So similarly, creation of harmonic without digits. These were the conditions of our system without digits. Now we are in the previous we are dealing with IEEE for 14-bus system, but here we are dealing with the IEEE actual data. It's 11 point something, 8 point something, which this is the condition with digits. So this is the harmonics voltage spectrum without digit. So bus 1 spectrum, this is the overall spectrum, this is the bus 1 spectrum. Using single tune, now we have implemented the single tune on the IEEE, we implement this on the ISACR data. Now it's reduced to 0.6 THD. In the start it was a level, similarly 0.79, 2.0, which means that our filters are working completely. So here we have compare effects of single tuned filters. Without filters it was 6, but when we implemented this fifth harmonic reduced to almost to 0 point something. Similarly, we also suppress the other one, which means we reduce the total THD of the system using C-type filters. Of course, when we implement the C-type filters, these are the same condition. Where we want to show you that actually our filters that we have designed are working completely for the system. For bus 1, it shows on the different buses. So as I mentioned that we have used both C-types and single tune, but the issues using C-types and single tune that we have in single tune, we have depends upon the losses. In single tune, we have the losses, high losses. Like here we can see that for the same fifth harmonic it's 25.18, but similarly for the 11th harmonic it's 60.1, which means that it's double. So this is the issue that in single tune, the running time losses. If you are using your filters for the long time, which means that the losses will be, the running time losses will be increased. So if we have extra component in C type, but if someone can support financially then C type, so its running time losses will be decrease. Here we just compare both C types and a single tool according to their losses. This is the waveforms. Without filters, it's completely distorts. With filters, it's completely smooth, which means that our system is working perfectly. So in conclusion, we can say that we have investigated different systems. Which type of filters for which reasons you can use and which type of a topology you can use. So references is that we have used because we have studied different lots of papers for this research. By the grace of Almighty Allah, we are also funded by Ignite, National Gratitude Research Institute, and INGRI, National Incubation Hyderabad. But we are working here, so we are also funded by Ignite. So these are the posters that we are presenting at the last day. So thank you very much. Thank you to everyone that support us through our FIP, our supervisors and co-supervisor, and everyone that support us to our FIP process.